We're also going to talk a bit about actually activating the operating system, invoking system calls. So operating systems run mostly, as we've just discussed, on interrupts. In addition to interrupts that are generated by hardware and by devices, a keyboard signaling the F1 key has been pressed, there are also interrupts that are generated in software. And this is a way of getting the attention of the operating system and sort of saying what we would like to happen. This is how a user program asks the operating system to do something that it would like to do. And when we specifically invoke it, the software interrupt is referred to as, well, it's a trap. So trap is really just the name for the software-generated interrupt, and in addition to the idea that it could be generated intentionally to get the operating system's attention, there is also the possibility that it's generated by an error, like an invalid instruction or a division by 0 or something like that. And if it's simply an error, the operating system decides how to deal with it, and usually in a desktop or laptop operating system, the strategy is sending the exception to the program that caused it, and this is usually fatal to the offending program. Your programming experience maybe tells you that you can catch the exception. Maybe you've done C++, Java, C#, try catch kind of syntax. But usually an exception is unhandled and it terminates the execution of the program. It just dies. The more interesting case is the intentional use of the trap, which is to get the operating system's attention. And when a user program is running, typically the operating system is not. We could even say it is sleeping, in quotation marks. If the program needs the operating system to do something, well, it's got to wake it up. And when the trap occurs, the interrupt handler, part of the operating system, is going to run to deal with the request. And we've already discussed a little bit the idea about user mode versus supervisor or kernel mode instructions. Supervisor mode allows all instructions and operations. Even something seemingly simple like reading from disk or writing to console output requires the privileged instructions every time. These are super common, but anytime we want to do that in a program, the operating system has to do it for the program. And modern processors keep track of what mode they are in using a mode bit. And at boot up, the computer starts in kernel mode as the operating system is started and loaded, but regular programs, user programs, are started in user mode. And when a trap or interrupt occurs, the operating system takes over, the mode bit is set to kernel mode, and when it's finished, it goes to user mode before the user program resumes. So if you want to send output data to a printer, right, our user process is executing up until the point where we request to print. When we submit the request to print, this results in the trap. The mode bit is set to 0. The operating system wakes up. It executes the system call that says, oh, you want to send this data to the printer. The print fails because cyan level is low. We get back a failure result. Mode bit is set to 1. So we go back to user level, and then we handle the situation in the user level where we say, sorry, we were not able to print because you must construct additional pylons. You must purchase additional cyan. Okay, that's a very simple example, and it involves the operating system to make that happen. Okay, why do we have user and supervisor modes anyway? Well, as Uncle Ben said to Spider-Man, with great power comes great electrical bill. No, I got that wrong. With great power comes great responsibility. Same reasoning exists for this as to why we have user accounts and administrator accounts. The goal is to protect the system and its integrity against errant and malicious users. We've already talked about protection and the importance of enforcing the rules of the system. And so reading data and writing data, especially sort of outside our area, is going to be responsibility of the operating system, and to make sure that we do not let users do things that they are not supposed to do. So, yeah. There's lots of fun examples you could imagine if we didn't have this rule, right? Like if multiple programs are trying to use the same I/O device at once, if program 1 wants to read from disk, and this takes time, if program 2 wants to read from disk as well, the operating system forces program 2 to wait its turn. If we didn't have this enforcement, well, it would be up to the authors of Program 2 to check if the disk is in use and wait patiently for it to become available. That may work if everybody plays nicely, but sooner or later, somebody will be nasty, right? The world could be so beautiful if only everybody would cooperate. Where's my flying car? But sooner or later, there will be a program that does something nasty, like cancel other programs' read requests, so it gets to go first, right? I mean, you can't stop people from being jerks, right? There's no magic in this. Okay, but this doesn't come for free, right? Switching from user mode to kernel mode takes time. There is a non-zero cost to creating the interrupt, for handling the interrupt, returning from the interrupt, all of that kind of thing. It requires some instructions and it requires some time. And certainly it would be faster if everything ran in kernel mode because we would spend no time switching. But the security and the integrity benefits for this are considered to be worthwhile. And yeah, if you've read up about sort of design anti-patterns, you might be familiar with one of my least favorites that I see, and I comment about it on code reviews if I see it, which is exceptions as control flow. And this is what happens when you're using exceptions as a way of managing the execution of your program. A pretty common example would be something like, if you want to pay a bill or transfer money or something, if there's insufficient funds, you could generate an exception and you could throw it, but I don't like that because no is a valid answer, right? It's not totally unexpected that somebody might not have the funds in their account, and so we should actually have a better way of handling that with regular control flow, because that's less expensive than creating an interrupt every single time, right? Creating an exception and throwing it and catching it and all that is not nice. So the performance degradation, if you will, that is required for switching between user and kernel mode is considered to be worthwhile because it is more secure. And that is important as far as we're concerned in operating system design. Okay, so I would like to actually do a practical example when we are reading from disk in a Unix system call. And the example we're going to do is really easy. We're just reading some data. It's nothing super exciting. We're just interested in reading data from a file. And so the function that is provided here is the function prototype is read. It returns size t, and this is just a descriptor of the size of the data that has come back. It's just an integer. And we specify a file descriptor, a buffer, and a count. Retakes those three parameters. So the first parameter is the file. A file is opened using the open system call. We're going to talk about that in the next topic. But let's imagine that we have the file open already. This is the file descriptor is how we reference that file. The buffer is the destination where we're reading the data to, and how many bytes to read is how much data we would like to actually read. And read returns the number of bytes successfully read, so you can ask for 1,000 bytes, but if the file is only 250 bytes, you will get back you successfully read up to 250. If you reach the end of the file, then obviously the answer is going to be shorter than that one. So yeah, this is our system call, and this is how we would request data to be read into memory from a file. So this is a system call, and system calls have documentation, and finding and reading this information is a key skill for doing the kind of work that we plan to do in this course. As an operating system author, it's somewhat your responsibility to write good documentation such that people who want to call this function are able to understand what they need to provide and what they'll get back. And Google or other search engine of your choice is your friend, and you could look at man7.org, for example, as a location for the documentation of this. Other sources for other system calls. And so if you're uncertain about how something works, you don't know how to invoke this, you're not sure what to do, well, these are good things to look up, and it'll give you a long and detailed breakdown of here's everything that is worth knowing and here is what is supposed to happen, and here's the expected result, and here's the error codes that could happen if something goes wrong, right? Because that's also a possibility. Things could always go wrong. So let's take a look at what actually happens. So in preparation for actually calling read, the parameters are pushed on the stack. This is what happens when you call a function in C or C++ anyway. And read is called, so it's the normal instruction to enter into another function. And the implementation of this function will put its identifier in a predefined location, and it executes a trap instruction which activates the operating system. When the trap occurs, the operating system takes over, control switches to kernel mode, and the interrupt handler inside the trap handler inside the kernel runs, and it examines the request. It checks the identifier that was put in the register earlier, and based on that, it knows which system call it should be executed. This one we've said is a read. And so the handler will now execute the read, and the read will transfer the data from the source to the destination according to our wishes. And that is going to move the data. It potentially takes a while. But when it's finished, control is returned to the read function in user space. So we exit the kernel, return to user mode. Read finishes and returns the value, and control goes back to the user program. So if you wanted a system call sort of complex example, in this case, we will have just a little program that is capable of doing everything that we've just discussed. So we'll have our function prototype read file, which takes a file descriptor. Why? Because otherwise it wouldn't fit on the slide as nicely. We will also have here some niceties about telling the user how to invoke the program. So if the argument count is wrong, it'll tell you how to do it. We'll open the file. As I say, we'll talk about how to open files and how to use the open call in the next topic. And if something goes wrong, we'll print an error. That's fine, and then we'll read file and close the file. And for reading the file, we will define buffer size as 256. We will allocate a buffer of that size, and with a while true loop, we will memset the buffer, initialize it to 0. And then we will try to read from the file into the buffer, buff size -1. And if bytes read is 0, we've reached the end of the file, so we'll break out of the loop. Otherwise, we print this section of the buffer. You'll notice buff size -1. Why? Because it's a C string. We need a null terminator at the end of whatever chunk we have actually read. And so by memsetting the buffer to 0, we're making sure that we filled all the bytes with 0. And if we read up to 255 bytes, we can be certain that any bytes that weren't overwritten in this case, there's going to be at least one, will be a 0, meaning we have our null terminator on the string. And once we get to the end of the file, we print a new line, we print end of file, and another new line, and then we deallocate the buffer. So that's pretty straightforward. Right, the magic happens in the call to read here, where we specify this is what we're reading, because, well, we are pushing data onto the stack, the arguments, file descriptor, buffer, and the amount of data we'd like to read. And then we invoke the system call. The system call puts its identifier in a designated location. The trap instruction is fired. The operating system responds to the interrupt and examines this identifier. Runs the system call handler that matches the identifier. When it's finished, control exits the kernel, goes back to the system call, and then control returns to our user program immediately before the assignment statement here. And the next thing that happens is the assignment that returns the result here to the variable bytes read. So if we read 12 bytes because we were nearly at the end of the file, then 12 is assigned to bytes read once we have exited from the system call. So I hope we have a good understanding of sort of the process of getting the operating system's attention and how to get it to do what we want it to do. And in our next topic, we'll talk more about sort of working with files, because it's pretty hard to do most things that we want to do in this course if we don't work with files at least a little bit of the time. So let's pick up in that next topic.